Hello everyone, I want to talk about section 8.1, valence bond theory. The learning objectives for this section are: describe the formation of covalent bonds in terms of atomic orbital overlap, and define and give examples of sigma and pi bonds. So in that second learning objective, the symbols there are sigma and pi. So these are Greek letters, and I know we've seen sigma in other ways before. This is the lowercase sigma as opposed to the uppercase sigma. And we'll talk about how we're using it here shortly. So I want to talk about valence bond theory. So as I mentioned in the introductory video, we are going to sort of expand our models and create new models to answer questions that our previous models did not answer very well. So we have previously discussed Vesper theory as a way of predicting the three-dimensional shape of molecules. And that it works very well at that, and we'll see there's other ways of doing that as well. But what it doesn't do good at is saying why do we even have a chemical bond? And that's actually something we explored a little bit towards the start of Module 7. And we'll talk about it a little bit more here as well. And what we were discussing there was actually something that is called valence bond theory. And so the idea of valence bond theory, and I think the best way of showing this is by showing the diagram. Hopefully this diagram looks familiar. It's something we saw in Module 7, is we can imagine two atoms, and each of them has their electrons, and there is an attraction between the nucleus of one atom and the electrons on the other atom. And as they get closer together, that attraction leads to a decrease in energy overall. And we get this, this chemical bond forming where what's happening is the electrons on one atom are attracted to the nucleus of the other atom. Okay, so this is valence bond theory. And again, we kind of discussed this a little bit at the start of towards the start of Module 7. We didn't talk about how that relates to Vesper theory, which doesn't really address this. In Vesper theory, we're not looking at why the attraction is happening. We're looking at, well, given that the attraction is happening, how do the electrons minimize their repulsions from each other? So this is valence bond theory. A few things to point out about this is that we're looking at an overlap of the atoms themselves, and we're not really looking at changing what the electrons are doing. We're just saying when they overlap, we have this attraction from one nucleus to the other electrons. So we're looking at them basically overlapping to explain this. They do combine to form, the electrons, I should say, are kind of forming a pair of electrons, and that is also minimizing energy. I don't know if we're showing that here. Yeah, we're not really showing that here, but what would end up happening there is their spins would end up being opposed. So one would spin up, one would spin down to make that work. Okay, so we start out far apart, we come close together. When we get close together, we form a bond. Because we form a bond, that's every time you form a bond, it's lower energy than when you don't have a bond. Okay, and that's what this diagram is showing. So we have a bond here, we don't have a bond over here. These are the basic ideas of valence bond theory. Don't worry too much about the specific energy values. And then we have different bond lengths that correspond to various energies. Again, this is something we're not going to get into detail on in this course. One other thing we do need to talk about, and this will actually lead into the next theory as well, is the way in which the orbitals overlap. So based on their shape, what ways do they align together? And we basically, in our first example, we're assuming s orbitals, right? So we have two spheres overlapping here. When we have p orbitals, that overlap could look a bit different. We could have different possibilities. So we're showing showing what that could look like down here. So here we're showing p orbitals overlapping, and we're showing it happening in a couple of different ways. When we have the p orbitals aligned like this, so if you imagine a straight line that goes through the nuclei of each atom, we have the greatest possible overlap of those p orbitals. Whereas if we don't have that kind of straight line that goes through the lobes and the nuclei, I should say goes through the lobes and the nuclei, right? Because we can still draw a straight line here, but it doesn't follow the lobes. There's less of an overlap here. So this is the kind of overlap that results in the strongest bond. When we do this, when we have this sort of end-to-end overlap, we call this a sigma bond, okay? And the definition of a sigma bond is it's a chemical bond where the electron density is located between the nuclei. Okay, so between the nuclei, right in here. You'll notice that that would also essentially describe what's going on here between the two s orbitals. The electron density is between them. Electron density again here is between them. So that's what we call a sigma bond. Now you might be wondering, well, where else could it possibly be but between them? And we'll see what that is here in a moment. But for now, just recognize sigma bond means that electron density is located between the nuclei in the bond. One other thing I want to mention about this diagram before we move on is a notation that is important to understand related to bonding. And we use it with different bonding models, and that's how we're showing different colored lobes. And that's related to the wave function of the electrons. We're not going to get into a lot of details right now, but what we want to have happen here is the wave functions should match. So think of it like waves that are combining. They can combine positively or they can combine negatively. Here we're showing them combining positively because we have the same, basically the same sign of the wave function. We're indicating that with colors here. So we have the blue colors indicate one sign, the red colors indicate the other sign. And it's not necessarily that the blue is better than the red, but they have to be the same. So we wouldn't have a blue and a red overlapping here. That wouldn't work. That would lead to what we call destructive interference, which is something that another model gets into greater detail on. But we are using that notation here, so just be aware of that. When you see these different colors, that's what we're meaning by that. Here we're showing some other sigma bonds. So as I mentioned, we could have two s orbitals overlapping would also produce a sigma bond. We could even have an s and a p overlapping to produce a sigma bond. Okay, so notice here that they're blue, overlapping blue, and here as well. So we can have that happen. And then here they're overlapping p orbitals to give a sigma bond. Again, blue or red doesn't matter in terms of why it works. You could have had the p orbitals overlapping here be blue and the non-overlapping be red, and it would still work. Okay, so those are sigma bonds. The other type of bonding we'll talk about here are what are called pi bonds. And these happen from not an in-between, but a side-by-side overlap. And these will not occur for s orbitals, they will occur for p orbitals. So here we're showing what that could look like. So if we imagine two atoms that are fairly close together, And we imagine that each one of those has p orbitals that have maybe start out with a single electron. If we get them close enough, those p orbitals will overlap. Okay, so and again, the similar sign, so the reds together up here, blues together down here. And so the bond itself is not between the nuclei. There's no bond we're showing here. The bond is occurring up here and down here. Okay, so we say that there's a node along the axis between the nuclei. So there's none of the electrons in this bond are located there. There could be other electrons there, but not the electrons from this bond. So the overlapping p orbitals create a bond that is on either side of the internuclear axis. So we call that a pi bond. How this works is that when we have a single bond, it will generally be a sigma bond. So here we're showing one sigma bond. There's some complicated things that happen in more advanced, you would learn in a more advanced chemistry course, like a graduate level course, where you could have something going on where it's not necessarily a sigma bond. But anything in this course, if you have only one bond, it's a sigma bond. So that's, in this case, we would have the s orbital and the p orbital overlapping, and there are no pi bonds. When you have multiple bonds, those additional bonds are pi bonds. So you have one of the bonds is sigma, any others are pi. Okay, so 1 sigma, 1 pi here, 1 sigma, 2 pi here. So when we are counting bonds, we can also count, well, what kind of bonding do we have? One thing I do want to mention about this table is, and we're not going to get into the details here, but the energy going from single, so we can see it here, single to double bonds, isn't quite doubled, right? And that's because the energy of the pi bond is less than the energy of the sigma bond. So it does go up. It doesn't quite double for that reason, because it's not reproducing the same thing, it's creating something else that is similar. So be aware of that, but don't worry about the numbers or calculations. So just kind of qualitatively be aware of those numerical trends. So each pi bond is usually a bit weaker than the sigma bond between the same two atoms. So there's some examples here of counting those, so you might want to try that. The ideas in this section will be built upon as we move into section 8.2. So make sure you understand sigma bonds and pi bonds before moving forward.